Alrighty, welcome back to operating systems for the last and final time. So, this one, it's all just review. So, before I start, just so you know, your functions you're given, exactly the same as 2024 winter ECE344. You will get all these functions. So you get listed, your exams closed book, yada, yada, yada. All right, what do we want to do? Any suggestions or? Locking problems, all right, good. Any locking problem in particular? One from this exam, the previous exam? All right, well, let's see. So, I put a green check mark next to everything I did in section 1, so you can look at that recording, so you can see those questions if you want. Locking. Want to just do this question? Sure? Yes? All right, so let's make this a bit bigger. Whoops. So locking, examine the provided code where two threads executing thread 1 or T1 and T2. So we got two threads, we got a T1. Oh, it's this room. Oh, I hate this room. All right, we got T1 running. We got T2 running. They would both start running at the beginning of the function. All right. It says each acquire and release multiple mutexes. We have 3 mutexes in total, M1, M2, and M3. First part says, analyze if the two threads executing functions T1 and T2 in the provided code result in a deadlock. Explain the reasoning behind whether or not a deadlock is possible or not in this scenario. So, T1 will acquire M2, then M1, and then thread 2 will acquire M1, then M3. Do we have a deadlock? Yeah.
No, we do not.
No, we do not. That is correct. Why?
Because M1 will eventually unlock at the end of T2 and then T won't be able to continue.
So if thread 2 executes first, gets M1, I could still do the first call in T1. M2 is not shared between them. And then, if this one has M1, this one will try and get thread 1 will try and get M1, but it's fine. Thread 2 can make progress, get M3, do whatever it needs to do, carry on. Basically, if I want to do it succinctly, if I look at the dependencies, there's no circular weight here, right? I always get M2 before M1, and I always get M1 before M3. So there is no circular. So basically, the only two things we need to be concerned about for deadlocking, two things we can do anything about, is hold and wait. There is hold and wait here, but we need all 4 conditions for a deadlock, one being circular weight. In this, there is no circular weight because we have M2. We need to get M2 before we can get M1, and we need to get M1 before we can get M3. So those are straight lines. That is not a circular weight. Yeah?
What would it be like if we would have circular weight?
Then we might deadlock.
No, I mean, like, what is an example of circular weight if we change something like that?
What's an example of circular weight? Well, luckily enough, it says, assuming an addition of a third thread, thread 3, executing function thread 3, devise a sequence of lock calls here involving only mutexes M2 and M3 that could lead to a deadlock. So we probably want hold and wait to happen. How would I lock M2 and M3 that would result in a deadlock here? So going here, these are the two functions I have. I'll just write it here just for sanity, I guess. So say we have thread 3, and I really dislike whatever weird electrical crap happens in this room. All right, so we want to use M2 and M3 in thread 3 such that it deadlocks. So what sequence do we want? Yeah.
Probably M3, M2.
Probably M3, M2. Basically, we want to create this line, right, to make our circular dependency. So that would mean I have to have M3 before I try to get M2. So if I add it here, I could just lock M3, lock M2. And then it says, describe this sequence and explain how it results in a deadlock combined with thread 1 and thread 2. So how it could work now is, since I have thread 3, what could happen is thread 1 acquires mutex 2. So this thread now has let's do it in orange. So this one has M2, and then we context switch to another thread. Maybe we context switch to thread 2. It acquires M1. So now it has the M1 mutex. And now we context switch over to thread 3. It gets the M3 mutex. And now none of them can make progress anymore, right? M1, or thread 1 can't make any progress because it's trying to get M1, which is held by thread 2. Thread 2 can't make any progress because it's trying to get M3, which is held by thread 3. And thread 3 can't make any progress because it's trying to get M2, which is held by thread 1. So we deadlocked. So everyone okay with that? So that was a very quick 18 marks, yeah.
Does that imply that if we want to add thread 3, we need to add another mutex to avoid a circular wave?
No.
So we can avoid a circular wave without, like, to do the thread 3?
So in thread 3, if I flip those two lock calls around, would I deadlock? No, right? Because now I don't have a circular weight anymore. So if I flip these two around, right, I do, whoops, I took too much. If I flip these two around, there's no situation where I can deadlock because now I don't have this, right? I essentially created this line, which is still ordered. So I still always acquire things in the same order. So I have no problems whatsoever. So there's only one sequence that will deadlock, and I was nice saying, well, I constrained the problem a lot. All right, so everyone okay with the locking question? All right, what's next? So we can, the hard threads question, let's look at the other exam for fun. Oh, yeah?
We do a Semaphore's question.
Semaphore's question. So let's start it on the other exam. So something like this. All right, Semaphore's question. So this is from the 2024 winter, yeah. All right, so it says, you are given 4 threads that get properly created and run. You want to ensure ordering between them. You decide to use semaphores to accomplish this task. Recall that semaphores, after initialization, use post to increment the value and wait to decrement the value, waiting until that value is greater than 0. Assume no errors occur, so you never need to check return values. Consider the following code. So I get 3 semaphores created for us that don't have any values, which hinting that I probably need to set them at some point. And then I have thread 1 to thread 4 all calling some functions, and then some comments that say F2 should only run after F1 completes, F3 should only run after F1 completes, then it seems like F4 can run whenever. Well, I mean, we have this dependency, so within a thread, it would call F3 before F4, but that's my dependency within a thread. And then it says thread 4, F5 should only run after F2 and F3 complete. F6 should only run after F4 completes. So first part, which is most of the question, says, fill in the initial values for each semaphore and insert a post and wait calls in a way that ensures ordering in the comments. You cannot change the ordering of the F calls, and they always execute in the order written within a thread. Write your answers on this page. Oops. All right, so basically with this, for every kind of ordering you want to ensure, just use a different semaphore. So we will start off with the ordering that waits for F1 to complete. So let's use semaphore 1 that should only wait until after F1 completes. So easiest thing to do with the semaphores, I find, is to first place my wait call. So what threads do I need to wait for F1 to complete? None. Well, yeah, some. So thread 2 and thread 3 need to wait for F1 to complete.
I thought you meant like who F1 is waiting for.
No. So I need to place a wait call. Where do I need to place one wait? Yeah. Above F2. So I need a wait here. Oh, curse this room. So wait with sem1. Do I need another wait or am I done? Yeah. Above F3, so wait on the same semaphore. Then next thing I like to do I need any more wait calls? Anything else need to wait for F1 to complete? Nope. So easiest thing to do now is to set the initial value. So the initial value you can think about is how many threads should be able to pass wait without any other thing calling post. So what should the initial value be in this case? 0, right? We don't want either thread 1 or thread 3 to start executing past their wait before thread 1 does something. So we need to initialize it to 0. And then for posting, well, we post after F1, right? So we post after F1. That's our dependency. So we post sem1 here. If I post sem1, that would increase it from like 0 to 1. That would only let 1 pass, right? Yeah?
Wait, so what exactly does the initial value do?
So the initial value, if I set to 0, right? That means that if thread 2 happens to execute first, since the initial value is 0, it's not going to make it past this call. It's going to get blocked, right? Until someone increments it. And similarly for this. If the initial value was, say, 2, then both the threads could just pass by wait, no problem. So that's why it's good to think about it. It's like, hey, without any posts, that's how many threads can pass by a wait. Because first one, go from 2 to 1. Next one would go 1 to 0, no problem. So that's why we have our initial value at 0. All right, so then we need to post after we call F1. Is that it? Just one post? I need another post, right? Each post just increments it. So I'll have 2 threads waiting for it, so I need to post twice in order to resolve it. So I need, wow, holy, I do not like this, whatever the hell happens in this room. All right, so I need to post sem1 here. So that is that first condition, right? So now both thread 2 and thread 3 will run after and only after F1 is done. So that's my first condition. So that's check. Don't try and reuse semaphores or anything crazy like that. So that means I could put a little check here. This is a check. This is a check. Now, next one, I want to only run after F2 and F3 completes. Yeah.
We just do like have 2 waits after like sem2 in front before F2 F5, and we add one post at each of the end of F3 and F2.
Yeah, so how I can do this one is it needs to run after F1 and F2 completes. So I'll need at least a wait here, and let's say I use sem2. So that's probably good. I need at least a wait there. The initial value should probably be 0 again because I don't want this to run until someone else posts. Then, well, now I have to insert my post calls. So I want to make sure it runs only after F2 and F3 completes. So they're in different threads. So I would need to post here after F2 and post after F3. So how I have it written right now, since I only wait once, well, either of those threads would be able to post, increment it, and then I could call F5 when either F2 or F3 complete, because I don't know which one will go first. If I want to wait for both of them, well, I just need to insert another wait call here. So now I wait twice. Each other thread posts once. So they have to both post before I can get by 2 waits. So is that okay? So that should check that one. And then with the last one, so I should only run after F4 completes. So again, I would just do a wait on sem3 here. Initial value should be 0. And then I could just do a post of sem3 right after doing F4. So are we okay with that? All right. Then the last one says, for each function state, what functions could run in parallel with it, not including itself? Write one if it can only run by itself. So should be able to look at this and see F1. In this case, F1 needs to complete before F2 or F3. Wow. Before F1 or, ooh. F3 completes, and then, well, F3 has to wait for F4 because it's in the same thread. Ugh. Then for F5, it can only run after both of these complete, right? So it only runs after both F3 and F2 complete. So this is F5, and then F5, or F6 can only run after F5 and also after F4. So that's all of our dependencies all at the same time. So if I'm running F1, well, it can't run at the same time as F2 or F3. So can't run anything else that's dependent on either of those. So F1 can only run by itself in parallel, right? Yeah.
In what case would we initialize something to non-zero?
So like our producer consumer example, where we wanted, like we had a buffer size, right? And we wanted at most buffer size threads running at once. That's when we set like the initial value to the buffer size so that we can have 10 threads go all at once, but they're capped at that. I can't have any more. That's generally, you'll usually see it initialize at 0, but sometimes you might not if there's some other weird limit or something like that. All right, so for this, you can only have F1 running by itself. F2 could actually run at the same time of F3, right? So F2 here, while this is running, we know F1 is complete, so we could run it at the same time in parallel with F3 from thread 3. Also, there's no dependency. It could also run at the same time as F4. So, and that's it. And then I shouldn't really have to go on. You can double check the answers with the other one. I'll try and move on to something else. Yeah?
From this, wait, are you moving on to
Oh, if you have a question, that's fine. Yeah.
so like the next one?
Oh, you want a next one or this one?
Are we done with this one?
If we want to be, yeah, we can be done with this.
Yeah. Can we do question 12 from this one?
Question 12. Okay, so I'll just do this question from the start to make sure everyone's on the same page. All right, so we got processes. It says, consider the following code. Assume all system calls are always successful, and we're running under process ID 100. So we have process ID 100 running. Whoops. So process ID 100. So we have this loop that executes 2 times, so this will be fun. So we go through the loop once. We have, oh, this will be really fun in this room. So we go into the loop, process 100, creates a variable called I. It's equal to 0. Then it calls fork. So it creates a process, process 101. It's an exact clone, so it has an I with the value of 1. And the only differentiation between them will be the return value of fork. In the parent, ret will be equal to 101. In the child, ret will be equal to 0. So then, let's say, for argument's sake, process 100 executes next. So currently, I is equal to 0, and ret is greater than 0. So it's going to get stuck here in the wait. So it's going to wait for its child to perish. So only thing I can do is run this child, which is 101. Doesn't look like 101, but it is. So no other choice. It has to call this print function. It would print, PID equal 101, ret 0, I is equal to 0, right? Then it would go up here, for loop, increments its I, well, ret went out of scope, so ret is dead, I got incremented to 1. Sorry, I deleted that, process 101. Oh wait, no I didn't. So now it calls fork again. So process 100. We'll draw the family tree up here. Process 100 created 101. 101 is about to create 102. So now we create process 102 from the fork. Here, I'll try and put them on the same line. So it's going to be exact copy of the parent, so it will have an I equal to 1. Only difference is going to be the return value of fork. So in 102, ret is going to be equal to 0. Process 101, ret is going to be equal to 102. Now, I don't know which one will execute next. I is not equal to 0, so that if statement will always fail. Don't know which one will execute next. So for argument's sake, oh no. Oh, I really hate this room. So don't know which one will execute next. Could be 101 again. That would print PID 101, ret 102, and then I is 1. Or I could have PID 102, ret is 0, I equals 1. So either of them will go ahead, come up here. Nothing is dead yet. Let's say P101 happens first. Both of their rets go out of scope. It would increase thankfully, mercifully, it would increase I equal to 2. Then it would drop out of the for loop and it can exit, right? So these are now mercifully both able to exit. I don't know which one's going to exit. 102 could die first, 101 could, doesn't matter. But as soon as 101 dies, then process 100 will be able to return, right? So then it will be able to pass by the wait because it would wait on only its direct child, which was 101. So it will then always print PID PID equals 100, ret was 101, I is equal to 0. And now process of 101 or 100 will come up here. I will go, so ret will go out of scope, I will increase to 1, and then it will fork again, create a new process, probably 103. Then 103, mercifully, it'll have an I, it'll equal 1. And then the only difference would be the return value of fork. So in process 100, it would return 103. In this process, it would return 0. And this is the last time they're both going to run. They'll both exit eventually. All right, so, whew. Everyone keep on track with all that crap. So, first question then, how many new processes get created? 3, right? We have that little tree at the top. So we assume process 100 always exists, so we created 101, 102, and 103. So next was draw a tree of the parent-child relationship showing the process IDs they would likely get. Yoink. Thankfully, we already did that. So next, using the PIDs in your tree, provide a possible sequence of outputs of the code. So we're going to see what? So these will eventually print too. So this will print PID 102, I equals 1. Or sorry, whoops, these are already dead, sorry. It's these two that will print. So we'll get PID equals 100, I equals 1, ret is 103, and the other one we get PID 103, I equals 1, ret equals 0, and then we'd get this line first always, then this line, then this line, and this line. That's a possible sequence of orders. You get 1, 2, 3, 4, 5, 6. So we get 6 lines in total. That's one possible sequence. All right. Oh, yeah?
Would 100 always print before 103? I thought 100 would wait for 103.
100 will wait for 103. No.
Because the I is not equal to 0 here.
Oh, right.
Yeah, I is not equal to 0. So process 100, this will only happen once. Process 100 will only wait for process 101. All right. So there's a possible sequence. Show an impossible set of outputs for the provided code. Ensure that all the sequence prints within the same process remains consistent, but the overall sequence cannot be produced by the code. So basically, just swap these two around. So what that's saying is, like, I'll always see process 101 ret I equals 0 and then I equals 1, and it won't somehow reverse within the same process. It's just between processes. So process 100, oops, sorry, this. Process 100 will never print first before 101 because it waits for it, so that can't happen. All right, now we can finally go to the other one. So for each direct child process of 100, which in our case, the way we wrote it was 101 and 103. State whether it will always, maybe, or never be a zombie or an orphan. One answer for each. Briefly describe your reasoning. So for process 101, can it be a zombie? And this is always, maybe, or ever. Is there a chance, even for a brief second, that it is a zombie? Yes, right? So why? Well, what might happen is as soon as process 100 forks the first time, we just immediately start executing that new process, 101, right? 101 can execute till it's completed. It terminates, it's technically a zombie. And then it will get cleaned up, so it will never be a zombie by the time process 100 exits, but it will be a zombie for a little bit until it gets cleaned up. I think I also, if you explained it well enough or if I thought what you meant, I also gave it full marks if you always said never. But you had to be clear that it never, if you assume process 100 exits. Was that your question?
It's for the other.
The other one, okay, so that one's okay, so let's finish this one. Maybe, briefly. All right, orphan, can it be an orphan? No, or never, because it gets waited on. Right, so the parent will never outlive it because it's always gets waited on and we don't assume anything weird with things dying. All right, for process 103, can it be a zombie? And is it always, maybe, or never? So, in this case, process 103, no one waits on it, and it can terminate before anything else, right? So it could definitely maybe be a zombie. I think that should be the answer. Yeah, so maybe, may, terminate before any. And the only thing that's going to wait on it is a knit whenever it gets reparented because nothing that I wrote explicitly waits for it. All right, the next one is orphan. So can it ever be an orphan? So an orphan, if we go back to our diagram, was it 103? So orphan means it's possible that process 100 exits before me, right? So in this case, is it possible process 100 executes before me? So the way I left this off is whatever process 103 was created, right? So it could be the case where process 103 is created. All it's going to do is print and exit, but it doesn't have to execute next, right? Right?
Like, my confusion is that 103, there's no wait getting for it. So, like, regardless of the termination, because its exit status isn't explicitly being read by the parent, does that always make it a zombie?
103 doesn't get waited on by anyone.
Yeah, so isn't it always a zombie? Or is zombie dependent on, like, the termination sequence, and it doesn't matter about its exit status?
Yeah, I think I also took, it gets a bit finicky with the zombie because technically, you know, if it gets reparented in it, it's going to get terminated at some time. It might be a zombie for a little bit, even if it's like for loop waiting. So I also accepted always for that one. So always was fine for that one. And then for orphan, possible that it could be an orphan, right? Might be an orphan because process 100 doesn't wait on 103 or anything. Process 100 could just print its line, terminate, and then as soon as it's terminate, it just orphaned 103, right? Could be the other way around where process 103 executes first, it terminates, so doesn't have to be an orphan. Although shouldn't that be always? Actually, it should be always an orphan, right? No?
No, because we can exit before 100.
Oh yeah, it could still be running, right? The opposite could be true. So 100, or we could exit before. Yeah, but if we exit before, we're done, but it doesn't wait on us, right? So eventually it's going to exit, and you're going to get orphaned, and you're going to be a zombie orphan. So I think technically the answer, I think the answer given was maybe, but I think it should always be always for orphan.
So if process 100 exits before 103, 103 will be orphan. But since 100 doesn't call away 100, will 103 always be on the orphan?
So 103 will always either be an orphan that's still running or a zombie orphan. So I believe the solution's wrong. It should always be an orphan because we never wait on it, right? So it should always be an orphan. I believe the solution's wrong. All right, next one. Yeah.
File systems.
File systems. Which one? This file systems one? Huh? All right, file systems. How much time? We got 14 minutes. So this file systems. Assume a file with a block size of this. So I'll just write powers of 2 because I like to. 4 byte to the power of 2. Damn this room. And 128 byte inodes, which is 2 to the 7. Yeah, 2 to the 7. Yeah. Inodes have 12 direct pointers, 1 indirect pointer, 1 double indirect, and 1 triple indirect. Analyze the output of ls, all the stupid arguments. The output of the format includes inode numbers in the first column. So these are the inodes. So it's telling you, just in case you forgot, the other ones should be somewhat self-explanatory. So this column is the number of hard links. Then user that owns it, group that owns it, although it doesn't really matter, the size, and then the modification date, which we cannot forge, right? Didn't show you how to do that. Do not write your whoever. And then finally is the names. So first question says, when editing file C, what inode's contents get modified? So the file C is a symlink. So it's symbolic link, so it's basically named to a name. So if we try and open it, it won't open inode 22 because that stores essentially B. So we're treating inodes as just named to a name. So to find the inode, it will then refer to the name B, and then look at that inode, which is inode 20. So inode 20's contents get modified. Everyone okay with that? All right, next one. Is it possible to store all the inodes associated with this directory on a single block? Provide an explanation supporting your conclusion. So we can figure out how many inodes we can fit on a block, right? So the number of inodes we could fit on a block is just the size of a block, so 2 to the 16, or 2 to the 12, sorry, divided by the number, the size of the inode. That's the number of inodes per block, which thankfully I already wrote everything out in powers of 2. So that's just 2 to the 5, which is equal to just 32. So that means I could fit inodes 1 to 32 on a single block, right? If I look at my inode numbers here, they all fall within that range, 1 to 32. So the answer is yes, it fits. All inodes. Wow, that's, hopefully you have better writing than me. Fit between 1 to 32. And my writing's usually better than this, but this room's cursed. I have to write like a goblin. I don't know why I thought that. All right, next one. Determine the number of data blocks that file E will occupy. So File E, its size is 5,000. So can I fit 5,000 bytes on a single block? No. How many blocks do I need? 2, right? I need at least 2. So 1 doesn't fit, but 2 fits. They're each 4,096. So if I have 2 blocks, that's like 8,192. So the answer here is just 2. Then it says calculate the number of bytes lost due to internal fragmentation for file E. So 2 blocks is 8,095 bytes, or you could just say 2 times 2 to the 12. Again, I don't really care if you have a calculator as long as you have the right numbers. I don't care. So it's just that minus 5,000, right? So could write either. If you just stop there, that's fine. If you have your blanket calculator with you, that makes you feel safe. You can do the final calculation if you want, which is what, 3,192. Easy calculation if you don't have your calculator, but you could use it if you want. Doesn't matter. So that okay with everyone? All right. Next one. Determine the number of directories contained within the parent directory represented by inode 19. Describe the name of all the directories linked to this inode. So that's inode 19 is a directory, and it's the parent of this directory, right? So, well, I know that, let's give it a name. So let's just say, I don't know, let's call it directory D1, I don't know, some mystery directory, right? So in some place in directory D1's parent, it will have an entry that has like the name directory D1 19, right? So it will have a name in some other directory, maybe the root directory, maybe, I don't know, some other directory, who knows. And then inside that directory, right, it will also have a name period that points to itself, right? And then in every other directory, it will be the parent of that. So everything else, whoops, nope. So in everything else, in any other directory, like, I don't know, call it C1, it'll have a ... to 19, for example, that one, the one we're currently looking at. And then every other parent or every other directory inside of it will also increase the link by 1 because it will have a ... that will refer to it. So every directory by default is going to have a link of 2 because it will have a ... referring to itself. Also, it will have a name somewhere else that refers to it. So an empty directory will have 2. And then every other directory in that directory will increase the count by 1 because it will have a ... that points to it. So another way you can think of it is just like that. So if the total link is 5, well, it has the default 2. And then for every other directory inside of it, it will have a ... also referring to it. So it would have 3 directories in total within it. So I don't know what their names are, so C1, C2, C3, whatever. So that okay with everyone? Sweet. All right, next one. What occurs when you execute RMB? Is it possible for the file to be deleted? So let's see. Let's get rid of some of this crap. So if we remove file B, what happens? Yeah, it just removes the name from the directory. So file B refers to inode 20. Well, file A also refers to inode 20, right? So if I remove B, all it does is remove this entry in the directory, and now it's no longer pointing to inode 20, but file A still is, so it's just going to decrease the count here to 1. So that file is not actually going to get deleted because there's still a name that refers to that inode. So, is it possible this file to be, so remove name and then not deleted. All right, assuming B is removed, what is the impact on C and the associated inodes? So, B is now gone. Does anything about C change? No, it just looks a bit red if you had color in your terminal, because C is stored on inode 20, its contents is pointing to B. Doesn't matter if the name B doesn't exist anymore, you won't affect anything about C. So the answer is nothing. If file A is expanded to use 13 data blocks, are only 13 data blocks required in total for its contents? Explain the storage mechanism. So, it says we have an inode, and then we have in total 12 direct pointers, one single indirect, one double, and one triple. So, if this file uses 13 data blocks, all the way to 13, can I point to them all using just the inode? No, I could point to 12 of them, right? So I could point to 12, say this is up to 12. Now, how do I point to that last pesky block 13? Yeah, I need a single indirect block, right? So I need to create a block here. That's an indirect block, so it's just a block full of pointers. In this case, I only need one pointer from it to point to block 13. So in total, I would require 14 blocks, right? So 13 for data, and then 1 for single indirect. Everyone okay with that? All right, next one. How many total data blocks are needed if the file grows to 140 blocks? Explains the arrangements and the rationale behind it. So we got to do a bit of math. So we need to figure out here the number of pointers per block. So we have our block size from before, which is 2 to the 12, and we have our pointer size, which is 2 to the 2. So 2 to the 12, I hate this room. So 2 to the 12 divided by 2 to the 2, that's 2 to the 10. So that is also equal to 1024. So that's how many pointers I can fit on a block. If my file contains all of that, then I can refer to 12 direct. I have my one single indirect. And then that refers to 1024. So in total, that is 1040, right? Data blocks? Or can I not do math? Oh no, I cannot do math. So that's why maybe you want a calculator. All right, so that's 1036, right? So I still have 4 more blocks I need to store. So my single indirect one is full, so I need to do a double indirect one. So for a double indirect, I need one double. In this case, it would need to point to one single. So a new single, one single, which would just have, in this case, was that 4 entries that point to other blocks, so 4 data blocks. So in total, my data blocks here are 1040, plus I needed 1 block for the single indirect, 1 block for the double, and 1 block for a single referred to by the double. So in total, I needed 1043, right? Hopefully that's right. All right, so now we are out of time. So thank you for taking this class. Hopefully you enjoyed it. Good luck on Saturday. And remember, I'm pulling for you. We're all in this together.